Hello, welcome to Organic Chemistry 2341. We're going to go ahead and continue with Module 2. In fact, we're going to finish Module 2. And then there will be a Module 2.2 that we'll do starting next week, which is about IR spectroscopy. We're going to do that as well. And then we'll go into acids and bases after that. So Module 2.2 is not on Canvas, apparently, or it is on Canvas, and it's also in the, it's on Top Hat as well. So we can work with that as well. Okay, I'm gonna go ahead and share my screen with my iPad. Okay, and then I can put that down here. Oh no, I wanna put that here, all right. Okay, all right, so can we, I'll move that up there, all right. So could somebody ping the chat room to make sure that I can, that people can contact me? Okay, hi, thank you. All right, so the chat room's working. I've got the gallery view up here. When I look up here, I'm looking at the gallery view. Yo, okay, good. I was young when that came out, but okay, that's another story. All right, so where we left off last time, we were talking about the naming of different functional groups, and we've finally gotten down to the ester group. Now remember, I'm sorry, the ether group here. No, we were in esters. Yeah, we were in esters. All right, so we just talked about how to name esters. And esters are kind of based on the idea that you have a carboxylic acid as half your molecule, and then an alkyl substituent. And so we named it for that by taking it as our carboxylic acid derivative and giving it the O8 function. No, not that. There we go. The O8, literally OATE function, tells us we have an ester, which is a carboxylic acid derivative, with its general formula being ORR prime. So this is the alkyl substituent, and it's called the alkyl substituent. However many carbons you have, make it the alkyl substituent, name for that, and that gives us our name there. Now, for our carboxylic acid, we have to count the total number of carbons in that carboxylic acid. And so it would be, if it was 6, it would be hexanoic acid, but we drop the oic acid and add the word 8. And so that tells us that we have an ester with whatever alkyl group attached to the oxygen of that carbonyl compound, or that carboxylic acid derivative. Okay, so that is the way to name our esters. And so we have, I'm going to go over this one more time here, that you always start numbering carboxylic acids from that carbonyl that has the C double bond O and the oxygen on it. See, that makes it great. You don't have any ambiguity. Carboxylic acids are always started on this carbon here. Sometimes people forget it though, because it's a double bonded to an oxygen, but it is your first one. And so you take your total number of carbons here, which is bute. And so we have butanate, we have bute, and we have AN because there are no double bonds. If we had a double bond there, it would be butenate, right? And so in the general form, R or R prime just means that they can be the same or different R groups. I just didn't want to define them. Okay, so anytime you see an R in a generalized structure, it can be any alkyl group. Okay. So in this case here, we have this R would be 3 carbons long, but because we have it in the carbon chain, it gives us our butanoate. This has 2 carbons on our other alkyl substituent, and it's called out separately. So it's ethyl space. This is one of the few times you use a space, and butanate, and that gives us our name for there. Again, if this had a double bond in it, it would be butene-08. If it had a triple bond in it, it'd be butyne-08. So that AN is all about the carbon-carbon nature. So we have our prefix, our infix, and our O8 is always our suffix, changing the functional group name, okay? And this is just a substituent, okay? Is that clear? Okay, so in every single word we have in our nomenclature, you can break it down into things attached, which are the substituents, the suffix, which is the parent number of carbons, the infix, which is do you have single, double, or triple bonds, and then the name of the functional group is at the end always. So always look for all those different parts in all the names, and you'll start to see the pattern and get very familiar and get it right more and more of the time. Okay?
So I have a question.
Yes.
Is there an inherent reason why there's a space there?
It's to signify that that is a substituent.
Okay.
And so notice in all the other ones, we'd have a name like a number, like a one something, and then they kind of run together. This is unique because the ester is kind of separate from the rest of it because that little group is attached. And so that's why it's done this way.
Okay, thank you.
And it's only the ester that does this. So that's why I drew your attention to it.
Got it, thank you.
All right. So then we started talking about amides, apparently. I thought I finished on, oh, I did. I finished on it. I must have done some note taking on here. So the next thing we have is amides. Amide is also a carboxylic acid functional group, but instead of having an OH there for the carboxylic acid or that O and an R group for the ester, we actually have a nitrogen now. Okay, and so that nitrogen tells us that we bonded to our carbonyl here. Oops, yeah. Oh, where's my pen? There we go. Okay, bonded to this carbon here. And notice if this was an OH, that would be a carboxylic acid because the carbonyl's here. Now that we have that N there, we've changed the name to amide. Okay, so it's not amine. Amine has an N in it and is not attached to a carbonyl. That D signifies that we have the nitrogen attached to that C double bond O, that carbonyl. Okay, all right. So that being said, the 1 and 2 carbons are substituents. Is the question for this slide right here, Brian? Oh, in the other example, let me. This right here, the red 1 and 2 here, that is the substituent, and we name it as a substituent chain. So it's the total number of carbons, and add the YL. Okay. All right. Thank you. I wanted to clarify. All right, let's get back to these amides here. So the amide is that AMIDE. The D means that you're on this carbonyl right here. And it's a carboxylic acid derivative, so you know exactly where to begin, right? We're going to begin with that carboxylic acid carbonyl, and we're going to count out from there. So in here, we have a total of 5 carbons. So if we didn't have all these functional groups in there, it'd be pentanoic acid, okay? So now we know it's not pentanoic acid because we have it there. It would be pentamide, sorry. But pentane amide, okay? Pentane, sorry. I stumbled on that a little bit. Pentane amide, okay? But the AN here is our infix. And in this compound, we actually have a double bond, so we have to change that infix to an ene, okay? And we have to locate it. So it looks like that ene is starting on our 2 carbon here. So that means we have to have a 2 ene, and then our amide is still on the end for our functional group. And now we can look for the rest of our materials. We have our penta, we have our 2 ene, and we have our amide. So now let's look at our substituents. Looks like we only have the 1 substituent, which is a hydroxy, and it's on our 4 carbon. So the only thing we have left is stereochemistry, okay? We have 2 things attached to our double bond. When we have those 2 things attached to our double bond, we have to see if they're on the same side or the opposite side of the axis going through both carbons of the double bond. And in this case, we have 1 on this side and 1 on this side, so that makes it trans. So let's put the whole thing together. We have trans -4 for the hydroxy being on located 4, hydroxy pent for the 5 carbons in the parent chain, 2 ene for the double bond, amide for the functional group, okay? See how we follow the same rules every single time, and just we can locate everything exactly where it goes. Okay, now amides have a unique function like amines. in the fact that they have different classifications based on how many carbons are attached to those amines, okay? So I'm gonna skip that slide and come back to it. No, I don't. Okay, wow, I didn't have it. Okay, so because we can have different things attached to that nitrogen, oh yeah, I can do it here. I think I had somebody in office hours that I was playing with this on. So. Okay, so now we can have different types of amides. The first type of amide is the one where we only have the carbonyl on a nitrogen and it has two hydrogens on here. We call that a primary amide because it has only one carbon bound to that nitrogen. In this case here, we actually have an opportunity for substituting one of those hydrogens for an alkyl group. If we substitute one of those hydrogens for an alkyl group, we still have one carbon here and one carbon here. So that makes this a secondary amide. Yes. No, trans meaning opposite, yeah. All right, so what if we actually took this hydrogen off and put another alkyl group here? Well, that would turn it into a tertiary amide, okay? So that tertiary amide or a secondary amide will always have a weird thing you have to locate that alkyl group just like in an ester. But unlike an ester, you are gonna locate it to say it's attached to the nitrogen by putting an N instead of a number, okay? So let me do that again with just the compound we have. So we have a primary, which only has the carbonyl, a secondary, which has a carbonyl and an alkyl group, and a tertiary, which has a carbonyl and two alkyl groups, okay? So we have to know how to name those. So anytime you have one of these secondary or tertiaries, we've got to figure out what our attached species here is and put it in the right place. So this species is our methyl group, okay? But it's not on the carbon chain. And so we're going to tell them it's not on the carbon chain by putting an N here. So that methyl group is actually attached to a nitrogen. So that's where this N-methyl comes from, okay? So kind of like where we had an alkyl group on that ester, where it's signified by that space, in this case, we're actually signifying it's on a nitrogen. So again, with a carboxylic acid, you always start numbering at that carbonyl carbon. We have a total of 6 carbons. So that's going to give us hexenamide because we don't have any double bonds. So hexa for 6, and for single bonds, amide for the functional group. Now we have 2 substituents. We have the substituent on the nitrogen, but we also have a substituent on the main chain. So we locate our substituent. So we have a 3-ethyl, okay? And just like before, we have to do it in an alphabetical order. Ethyl comes before methyl. So our total name is now 3-ethyl because it's located on the parent chain. N-methyl because it's located on the amide nitrogen. Hexa for 6, A, and for no double bonds, and amide, okay? So if we had 2 methyl groups on here, we would actually go N, N dimethyl hexenamide, okay? All right, questions on amide there, okay? So we did that one, we did that one. Now let's do this one. We're gonna put all those rules together, okay? And this one is a tertiary, okay? And so what we're going to do is we're going to use all the rules in correct order. And we're going to first identify our parent chain. Oh, look, here's a carbonyl attached to a nitrogen. That's our functional group, amide. Okay. Now we know that this is our number 1 because that's the carboxylic acid. So we number it to 6. So we have hexa, hex. But we have a triple bond. So we have to locate our ine in there somewhere. So this is going to be hexyneamide, but we still have to give it a number, okay? So our numbering from here, our first carbon of our ine is on 3. So now we have hex 3-ine-amide, okay? Do we all see where that came from?
I have a question.
Yes.
Where the YN, where did it come from? The iron?
Y? The
Yeah.
YN comes from the fact that we have a triple bond in our chain. Because AN means we only have sigma bonds. EN means we have one pi bond. And YN means we have two pi bonds. And so that means we have a triple bond has two pi bonds, and that's where the YN comes from.
Okay, thank you.
Okay. So we have, let's see, we have our 6 carbons, we have our triple bond, we have our amide, and we've located our triple bond. Now we can play with the alkyl substituents, okay? So the alkyl substituents are, we have a methyl group here and a methyl group here, okay? So we have 2 methyl groups, so we can say dimethyl, but we have to locate them. So we also have an ethyl group here, and it's located on the nitrogen, okay? So ethyl comes before dimethyl because it really, we don't use the di. And so we have to say the ethyl group is on the nitrogen, okay? Followed by a dash. One of the methyls is on a nitrogen, but the other one is on the 5 carbon. And then we have dimethyl, hex 3 ine amide. Okay. So
I
see,
have another question.
yes.
Sorry. So like when naming it, does the N come before the number? Like for the dimethyl, does it, like what if we switch it? Would that be wrong?
It's more appropriate to put the N first.
Okay.
But if you swapped them, I would probably understand what you meant.
Okay, thank you.
But it's by IUPAC rules, the N comes first. Okay. But notice, because it's a locator, because it's a location, we have that dash, comma, number or letter dash. Okay. That's telling us it's at a position. That those numbers and letters are telling us position. Just like this tells us position and this tells us position. Okay. All right. So the next carboxylic acid derivative we have is what we call the anhydride. And imagine the word anhydride means without water, right? So imagine you took 2 carboxylic acids and took away water. That's what this is. So you can imagine if we broke this apart, we added water to it, we'd end up with 2 of the same carboxylic acids, because we would add an OH to one side and an H to the other side. And so that's why we call it an anhydride. So to name this, because it's still a carboxylic acid, but it has lost water, we call it an oic anhydride. So instead of carboxylic acid or hexanoic acid, it's going to be hexanoic anhydride, signifying that you actually have 2 of them linked together. Now, if it's symmetrical, you're done, because all you have to do is name one side, and if you don't specifically call out a different name for the other side, it's assumed to be symmetrical. Okay, so notice here we have 3 carbons on this side, 3 carbons on that side. So each side is a propionic acid, and that's made by removing water to give us our anhydride. If it's an unsymmetrical, then what you have to do is you actually have to name each one independently and list them in alphabetical order. So the way you do that is you cut through the center here, and you figure out how many carbons would be on this carboxylic acid. Then you would figure out how many carbons are going to be on that carboxylic acid. So this would be pentanoic acid. This would be propanoic acid. And now we list them in order: pentanoic, propanoic, anhydride. Okay. So if they're symmetrical, you just need one name. If they're unsymmetrical, you need 2 names.
Is that alphabetical order?
That is alphabetical order. When in doubt, alphabetical order. Okay. All right. So then there's another cool group we have. Remember when I said we have the carboxylic acid and their derivatives are where we have carbonyl compounds that have something other than carbon and hydrogen on them, and usually we're an electronegative atom. So in the carboxylic acid and anhydride and ester, that was an oxygen. In the case of the amide, that was a nitrogen. Okay, so the next electronegative atom we have to deal with is our halogens. And so we can actually have a halogen directly bonded to that carbonyl to make a very active group called an acyl halide. Okay, and so the way we name those is we have the carboxylic acid derivative name, we drop the oic acid and add the name oil and whatever the halogen is. So if you have a bromine, it would be oil bromide, or in the case of a chloride, it would be oil chloride. So if we had a hexane, a hexawyl chloride, pentawyl chloride, oil chloride. Okay, so that means that we have to, it's still named for that carboxylic acid. So we'll name this thing right here. We have our carboxylic acid carbon here. We know the end of our answer is going to be oil bromide. Okay, and we have 4 carbons in here. So that's going to be bute. Okay, but we have a double bond. And we have to locate that double bond on carbon number 2. So we have butene. So our 2-ene is the infix. Our bute is the total number of carbons on our parent chain. The oil is our functional group. And we have to decide what kind of structure our double bond has. We draw our axis through both carbons right here. Both substituents are on the same side of that axis, so it is cis. So when we build our whole name together, it's cis dash, and notice the cis is italicized, and then bute 2-ene oil bromide. Okay, let's see, I have a question here. In the case of acid anhydrides, will there not be a case which we need to specify the location number on a parent chain? There might be, however, it's hard enough to name acid anhydrides that it's very rare. Most of them are just symmetrical anhydrides. It would be rare to find anything else. And then you just have to look up that name because there's some subtle rules, but it's outside the scope of our class. Okay.
Thank you.
All right. So we had the different carboxylic acid derivatives. We had the carboxylic acid, we had the ester, we had the amide. We have 3 types of amide: primary, secondary, and tertiary. We had acyl halides, which are very reactive. So our next carboxylic acid, derivative, we already did nitriles, and nitrile was our other carboxylic acid derivative. So now let's get on to a different functional group, amines. Okay, and amines are like amides in the fact that we have the classification of primary, secondary, or tertiary is on how many carbons are bonded to the nitrogen. So that's the reverse of carbon and alcohols. This is all about the nitrogen on both the amide and the amines here. So in the case of one functional group and 2 hydrogens, one alkyl group and 2 hydrogen, that's what we call our primary amine. Okay. Now, technically, if you have no carbons on there, you just have ammonia, which is 3 hydrogens here. There's no carbon and hydrogen bond there, so it's not an organic compound. So technically, it's an organic compound. So it just has its own name, ammonia. Okay. Now, when we have 2 carbons bonded to it, carbon here, we now have our secondary amine. Okay. So it's all about the number of carbons bonded to that nitrogen. And here we have our tertiary amine. Okay. So the interesting thing is that it changes the reactivity and it changes the name. Now, if we were to turn these into true Lewis dot structures, there's actually a lone pair on this nitrogen. So the shape of all 3 of these molecules is actually trigonal pyramidal, okay, with the lone pair sticking up on top. Okay. Now, because of amines have this characteristics, we actually have 2 ways to name it, okay? So the first way we can name it is if it just has a simple alkyl group on it, we can just say the alkyl group name plus the word amine, and they run together, okay? So in this case here, we have 2 carbons, which is our ethyl group, and it's just ethylamine. And then if you have 2 or more groups on there and they're different, you just put them in alphabetical order and name each of them, okay? So in the case here, we have a methyl group and an ethyl group. So we're going to do ethyl methylamine. Notice it runs together. Only esters have that gap. And here we have 2 ethyl groups and a methyl group. So we get to use the di-alkyl group functionality. So we have dimethyl, diethyl methylamine. So that's the first way to name amines, okay? Okay. The second way to name amines is when you have the amine in a longer group. When we have it in a longer group, we're going to use our more traditional IUPAC rules by finding the longest chain associated with our functional group. In this case here, the amine is our functional group, so it's going to change the name. So that is our functional group change. And we're going to try to locate it at the lowest number possible. Remember, we've changed the name here. We want to have this number be the lowest number possible, okay? So we've located our nitrogen here. So we have a total of 5 carbons. So we have pent. Right here, we have a triple bond. So that means we have to have a YN in here somewhere. And we have an amine, and we located at the lowest one. So we have 2-amine. Okay, so let's figure out everything else. Oh, we have one other substituent here, which is a methyl group located on 3. So now we can put all those things together. We have one substituent, so we start with that, the 3-methyl. Then we have the pent for the 5 carbon chain. And now we have to locate the YN. And it happens to start on that number 4 carbon. So we have -4-YN. And then we have to locate our name-changing functional group, our -2-amine, which gives us our full name of 3-methyl pent 4-ane 2-amine. Okay. Now, if we have additional functional groups, additional alkyl chains on our amine that's changing the name of the group, we have to signify those with that N. Just like in the amides, we're signifying where they are in the M. So let me go ahead and pull this up, okay? So we have our nitrogen attached to our longest chain here, possible. Looks like it's 8, okay? So if we count them up, that's 8. So we're gonna have an oct in here somewhere. Ooh, we have an alkene, so we're gonna have an ene in here somewhere. We have an amine, so there's gonna be amine on the end. And we wanna locate the nitrogen, the changing amine at the lowest level, so we have it on 2. And let's see, we have a chloride as a functional group, as a substituent. Let me circle my substituents in black here. We have a methyl substituent here. We have a methyl substituent here, and we have an ethyl substituent here. Okay, so this ethyl substituent is going to be an N-ethyl. Okay, this methyl substituent would also be an N right here, but we have, wait for it, we have a second one here. So we can use the dimethyl rule, but we have to locate both of them. One of them is on a 7 and one is on a nitrogen. So the way we do that is we go ahead and do our hyphen, our dash nitrogen, dash N, comma 7 dash dimethyl. So that's where that's coming from. We have to locate our, let's see, chloro comes before ethyl, comes before methyl. So that means we're going to start with our 6-chloro. So 6-chloro-N-ethyl-N, comma 7-dimethyl, octa-6-ene-2-amine. Okay. Now, do we have stereochemistry? There's a question in the chat room about cis and trans. All right, what's the rule on cis and trans? Okay, cis and trans is if you have 2 things and there are above or on the same side of the axis of the double bond, or that's not on the same side of the double bond. Well, okay, so we have different substituents on different things. However, look at the end here. There's no difference in priority from this methyl group to this methyl group. So we cannot prioritize by E and Z, okay? If we cannot prioritize by E and Z, we do not have cis, we do not have trans, we do not have E, and we do not have Z. It is actually does not have a stereoisomer, and that's why we have not identified it. Anytime you have a double bond where you have 2 of the same groups on one of those carbons of the double bond, it will not have stereochemistry because there is no way to differentiate between the E and the Z or the cis and the trans. Okay? All right.
I have a question.
Yes.
So I see so where it says N7 dimethyl,
Yes.
so there's a methyl coming off the N, there's a methyl coming off the 7, but isn't there also the methyl, like, I don't know how to, there's, I thought there's 3 methyls,
Okay.
but I'm only seeing, I don't know.
All right. Well, let's look at this. So all of these carbons are in the parent chain right here. Okay. So so we don't have to look at those anymore. Okay. Which tells me our substituents are the methyl group here, the chlorine here, and remember this nitrogen is naming the chain. So this is actually part of the main chain, which makes this a substituent and this a substituent. Okay, so do you still see that other methyl group?
No, okay, it's part of the parent chain.
So make sure that when you outlined your main chain, so you have the correct number of substituents. All right. So any other questions on amines? Again,
Wait,
go ahead.
can you repeat when we're not gonna use the cis and trans?
Okay. If you look at your alkene and you have something where it's like this, okay, that does not have stereochemistry because there's no priority. You have 2 hydrogens that are the same on this side. You have 2 methyl groups that are the same on this side. Therefore, you cannot use any of those rules. Okay. All right.
Just to
Thank you.
clarify, when you're numbering the carbons, you said that the amine group's always at the lowest numbered locant, right?
The amine or any of the functional groups tries to be at the lowest number possible. If the functional group is naming the compound, we try to make it always the lowest. For the carboxylic acid, it is always 1. Okay. So does this identify? So in this case here, well, you have 2 things attached to your double bond. Let's do it like that. Okay, so now you have 3 things. So you think you can go with the nomenclature. So we have our axis here, and so we have different things here. But we chop our molecule in half this way, prioritize over here. We have a priority of 1. If we try to prioritize on this side, we can't. They are equal. There's no difference in them. Ergo, we cannot assign stereochemistry. Does that answer the question? That's why this double bond doesn't have stereochemistry, because there's no difference in the 2 substituents attached to that 1 carbon. All right. All right, so let's go on to nitriles. This is the last of our carboxylic acid derivatives, okay? And I want to show you why it's one of our last. Just like in the acid anhydride, if we had an amide here with 2 hydrogens on here, and some carboxylic acid chain, and we removed water, we took out this O, this H, and ended up with a triple bond between that carbon and the nitrogen, we have the nitrile functional group. In fact, that's how we make it. We actually can make it by a dehydration of amides. So, which we won't get into until next semester, so don't worry about that. So the idea here is the nitrile, if it's the highest priority thing, it's also a carboxylic acid derivative, which means we start with that carbon of the nitrile, the carbon of the carboxylic acid derivative. I have a question. So every time there's a double bond with 2 things attached to it, the double bond, either substituent or carbon on the parent chain, we don't use cis or trans. If the 2 same things are attached to the same carbon of the double bond, yes. If the 2 things are attached to different carbons on the double bond, then no, you have to go through cis trans, easy. Okay. Okay, now, because this is a carboxylic acid derivative, what would you say if only single bonds for nitrile? for a nitrile is defined as a carbon triple bond nitrogen. Okay, so I don't understand the question. So this functionality right here is our nitrile functionality. And in this case, it's our highest priority. And therefore it names the compound and also starts the numbering here.
Yeah, but then let's say there's no triple bond with the 5 and 6,
Oh,
and the rest is only single bond, but like would be like before
and this
nitrile
right
still?
here, drop out and be an ANE. Yes. Okay, yeah, I'm sorry, I misunderstood. Okay, so let's go ahead and name our thing. So let's go ahead, we have 6 carbons, so we know we're gonna have hex in there somewhere. We have nitrile hanging on the end. We do have a triple bond, so we've located it on carbon number 5. So that's where the 5YN comes in. And now we have 1 substituent, 2 substituent, 3 substituents. We have dimethyl and a bromine. So we can go with the bromine first as the lowest. So that gives us 3-bromo-2,4- hex for our 6 carbons, 5-ine nitrile. Okay. So that E right there is, we always leave that E so that it doesn't have 2 consonants sticking together, but it's ine nitrile. Okay, so so there's always going to be that little E there. It's one of the weird ones that breaks the rule, but it's how it's done. Questions on nitriles? Okay, remember every single one of these compounds has substituents, prefix, which is number of carbons, infix, which is nature of those carbon-carbon bonds, and the functional group at the end. Look for each of those things in every single compound. Okay. Now, I want to draw attention to a special, let's see, what time is it? 12. Okay, I need to stop at 1:15. Okay. I want to draw attention to a special functional group here. And the reason is that this name is really thrown around a lot, and it's called the acetyl group. And the acetyl group is just this CH3 carbonyl, okay? And then this Z group can change into a bunch of different things. If it's an OH, it's acetic acid. If it's an amide, it's acid amide. If it's an aldehyde, acid aldehyde. If it's a methyl group, it's an acetone or acetone. Yes, the nitrile is the only N triple bonded to a carbon because that satisfies all its bonding. In this case, it's an ester. Notice there's the alkyl group space acetate. So that's the ester with our space in there. And then acetic anhydride, where we have a symmetrical anhydride. So that acetyl function, that CH3CO, we're going to see that a lot. We're going to use that as a very common group. Okay, so you should devote that to memory or knowledge. Okay, all right. So what if you have more than one of the same functional group? Okay, that means you can start using that di, tri, and tetra function just like substituents, but it must appear in your suffix, okay? So when we do that, we locate our functional groups, count as many of them up as we have, and then we use di for 2 of them, tri for 3 of them, tetra for 4 of them, but then we have to locate them. So let's look at our name here for this one right, ooh, not that. For this one right here, we have 2 alcohols. And the alcohols are the highest priority thing, so we're naming the compound for that, okay? So we're gonna locate them in our lowest numbers, which are here, and we only have 1 other substituent here. And so we're going to say, instead of being hexanol, we're gonna call it hexane diol, okay? So when we have 2 functional groups, we have to go with the di and whatever the name changer was. So diamine or diamide, okay? But we have to locate where they are. So that's what this comma 2-3 dash 2 comma 3 is. It's telling us we have 1 of the alcohols on the 2, 1 of the alcohols on the 3, and then we just locate our substituent here. So notice when we go to this di system here, we have the full name in the prefix, okay? So, but if we have a double bond, triple bond, it's also there too. Notice we have the full name of that pentyne in the prefix, and then we have the di, whatever the functional group was. So in this case here, we have a dicarboxylic acid. And so we're gonna put it so our substituents are in their lowest possible order, right here. And in this case, the alkyne is located before the substituent here. So that's why it's on the lower number. And our substituent's on the 4. So that's where our 4-methyl comes from. The pent comes from the 5. And we would say that pentane or pentyne, but we have to locate that alkyne since it's not at the end. So that's where our 2 comes from. And then dioic acid, because we have 2 carboxylic acid. Okay, so anytime you have the same two or more of the same functional group, it's the highest priority, you get to use that di, tri, tetra functionality to it. Okay, and all right. So that brings us up to naming any compound we want. So what are the rules? We find the highest priority functional group first. So in this particular molecule, we have, let's see, we have a ketone, we have an alcohol, and we have an aldehyde. If we go to our review chart, we'll find that aldehyde is our highest priority here. So that means we're naming it for the aldehyde. So remember, on an aldehyde here, we have an understood hydrogen sticking out here. That's what's the aldehyde, the hydrogen on that carbonyl. Okay. So if we have that, our parent name changes to al. We drop the E and add al. Okay. We have a double bond. So that means we have to locate it and put ene. So that'd be -3 enal. Okay, so we've named those. But now we have a carbonyl and an OH, but they're substituents. It's not a ketone and it's not an alcohol. So as substituents, this is hydroxide, this is oxo. So now we need to put them in alphabetical order. Hydroxy comes before oxo, and put our numbers on them. So that gives us the 3-hydroxy, -5-oxo, hex for 6 carbons, 3 because that's where our double bond begins, al because it's an aldehyde. Okay, now our stereochemistry. Okay, we have 3 things bonded to our double bond. So we have to do priority. And if we look at this right here, we have on one side, the oxygen is higher priority than the carbon here. So this is priority. If we look at the other side of the double bond here, we have a hydrogen and a carbon, and that carbon takes priority. So they're on the same side, which gives us bracket Z bracket dash 3-hydroxy-5-oxo hex -3-enal. So now you have all the tools in order to name any compound possible. All you have to do is go practice it and start recognizing these functional groups, understanding what the priority is, and how to put them together. The oxo is used for aldehydes and ketones when they are not the highest priority. If you go and use the table on the nomenclature review on Canvas, there's a row for when it changes the name of the compound, and there'd be al and on. But when it's a substituent, there's the next column over, and that next column over has substituents like oxo, hydroxy, chloro. And so that's where you're going to find those names like oxo and hydroxy. So that's the way to use that tool at your disposal under there. So it should be 5-oxo. Oxo is, so oxo is defining the ketone that is on carbon number 5. However, ketone's not the highest functionality. Highest functionality is the aldehyde. So the ketone is now a substituent, and we signify ketone substituents as the oxo. All right, any other questions? Because that's my last slide on module 2. Okay, next time we'll pick up on module 2.2, which is spectroscopy. Okay. So let's go and think about what our activity is. Okay, our activity is, I emailed that out to you. It's nice to have a paper or an electronic copy of it. What I'm going to do is I'm going to give you a set of instructions. I'm going to put you in breakout rooms. You're going to go to your breakout rooms in groups of about 6, and you're going to try to go through and name all of those compounds. So in, let's see, do I have it here? I should have it here. So on the activity, you have 2 parts of it. The first page of the activity, I'm going to stop sharing and pull up the activity and share screen. This one. So if we look at our activity, there's going to be 2 parts to it. There's going to be the first page is look at the structure and figure out what the IUPAC name is, including some bicyclos and stuff on there. And on the second half, you're going to look at the name and draw the structure. Okay. And I want you to do this as a team. Be nice, introduce yourself, talk through the different rules, make sure that everybody understands the rules that are being used, and you work through them each on their way. Okay. Okay, let's see. I can try that. Let me go ahead and get everybody broken out, and then I'll move you after that. Okay. All right. So that's what you're going to do. All right. Stop share. The next thing we're going to do is you're going to go ahead and after you've done this, even if you don't get done in the amount of time we have here, go ahead and finish it. And you're going to take a picture of it, make a PDF of it, somehow get it up to Canvas. On Canvas, there's a tab under Assignments. If you go down that tab on Assignments, there's a thing called Activities. Click on that activity and it'll ask you to upload a file. Go ahead and upload your answers to that file by midnight tonight. And you will get credit, or at least most or partial credit, for the assignment today. Okay. Any questions about our activity that we're going to have? I can answer some other ones in the chats after we get everybody broken out in their rooms. Okay.
Are we doing this for the rest of the class time, or?
Yeah, rest of the class time. If you have to leave, just try to get as much of these hours in as possible. And I mean, till our remaining time of. We have till 1:50, so you have about 30 minutes to do this. And so you'll get 30 minutes to try to do them all together. If you don't finish it with the group, go ahead and finish it on your own and upload it before midnight tonight. Okay? And always look to Canvas. Canvas is always going to have all of your assignments, our schedules, and everything. Okay? No, you do not have to include your name, your group members on there. All you have to do is upload it to Canvas. I actually prefer it to be uploaded to Canvas because then I can speed grade it, and this grade automatically goes into there. Upload it to Canvas, please. It's so much easier. Okay. Okay. Any questions about this? Okay. So there's going to be a button once you get into your room. I'm going to enable sharing for everybody. As soon as we start getting in our breakout rooms, you can share a screen and work together. That's great. There's also a whiteboard there. And then you can also, talk amongst yourselves. And there's a button there to ask questions. And I'll run from room to room. And it might take a minute or two because I'll be answering another question. But I can answer questions from room to room. Also, Marcus will be running room to room, your SI, to answer questions as well. Okay. Yeah. So let's see. So I'm going to. Oh, yes, I emailed the document. I'm going to stop.